Hello again, welcome back. Let's now talk about the magnetic field lines. Magnetic field lines provide a visual representation of the direction and strength of a magnetic field, whether generated by a bar magnet, a coil, or a solenoid. Some general characteristics of magnetic field lines are: magnetic field lines are directional. They always flow from the North Pole to the South Pole of a magnetic source outside of the magnet and loop back the South Pole to the North Pole inside the magnet, creating a continuous closed loop. The direction of the field lines indicates the direction of the magnetic force that would act on the North Pole of a test magnet if placed within the field. The density of field lines, or how close they are to each other, represents the strength of the magnetic field in a particular region. A high concentration of field lines means a stronger magnetic field, while a lower concentration indicates a weaker field. Near the poles of a magnet, the field lines are closer together, showing that the magnetic field is strongest at the poles. As we move farther from the poles, the field lines spread out, indicating that the field strength decreases with distance. Magnetic field lines always form closed loops. They do not begin or end at any point, unlike electric field lines, which start on positive charges and end on the negative charges. This loop structure reflects the fact that there are no magnetic charges or isolated magnetic poles, no magnetic monopoles in nature. Each magnet has both a north and a south pole. Inside a magnet, the lines run from the south pole to the north pole, completing the loop and reflecting the conservation of magnetic flux. The field lines around a bar magnet emerge from the north pole, curve outward, and enter the south pole. This creates a characteristic butterfly or dipole pattern. Around a straight current carrying wire, the magnetic field lines form concentric circles around the wire with the direction given by the right-hand rule. If the current is in the direction of the thumb, the fingers curl in the direction of the magnetic field. For a solenoid, a coil of wire, the magnetic field lines inside the coil are parallel and uniformly spaced, indicating a strong uniform field. Outside the solenoid, the lines spread out and loop around at the other end, creating a pattern similar to that of a bar magnet with a clear north and south pole. As a matter of fact, a solenoid with a current is equivalent to a magnet, and they are used as electromagnets, which you can use to turn on and off the magnetic field by turning the current on and off. Magnetic field lines are influenced by the presence of magnetic material. In the presence of ferromagnetic material such as iron, field lines become denser as they flow through the material due to its high magnetic permeability, effectively strengthening the field within the material. Conversely, the materials with low permeability like air or vacuum, field lines remain less dense, indicating a weaker field. Magnetic field lines never cross each other. If they did, it would imply that the point of intersection, the magnetic field would have two different directions, which is physically impossible. This rule ensures that the magnetic field is uniquely defined at each point in space. So we have seen that an electric current generates a magnetic field, and the magnetic field lines of a solenoid are the same as those of a bar magnet. This means that we can use a current through a solenoid to have an electromagnet. This is a magnet that we can turn on and off with a switch and turn on and off the current. If we look at two bar magnets, we observe that the same poles repel and opposite poles attract. This applies also to the electromagnet. More on this soon. Finally, the magnetic field of the Earth is generated by electric currents at its core. The core of the Earth is made of iron and nickel at high temperature and pressure. They behave as a fluid, and its motion generates the magnetic field, whose direction depends on the overall direction of this motion. Because this direction has changed over time, the north and south magnetic poles of the Earth have changed. Now we observe how the intensity of the magnetic field is decreasing, which points to a possible near switch of polarity.
What did you do?
What do you mean, what did I do? I just reversed the polarity. This is very expensive equipment, isn't it?
Oh, very expensive.
This is, of course, in geological terms. In summary, magnetic field lines provide a useful visual framework to understand both the direction and strength of magnetic fields, showing us how the field behaves around magnets and in various configurations of current-carrying conductors. Let me know your questions in the comments below, and may science be with you.
Reverse the polarity. It's not working.
We're both reversing the polarity.
Yes, I know that.
There's two of us. I'm reversing it, you're reversing it back again. We're confusing the polarity.